Assalamu alaikum. This video will discuss documents 2 of chapter 9, Action Potential. In the previous document, you have learned that a neuron at rest has a potential difference across its cell membrane. You have learned that this potential difference is due to the unequal distribution of ions caused by the selective permeability of the cell membrane. During this resting state, potassium and sodium ions passively diffuse along their concentration gradient through leak channels that are always open and need no energy at all. You have also learned that this resting membrane potential is maintained at -70 millivolts due to the active diffusion of sodium and potassium ions against their concentration gradient through the sodium-potassium pump that is powered by ATP. And for this document, you will learn how is a nerve message generated within a neuron due to the disruption of this resting potential. Let's consider the experiment performed in document A of your books. An axon of a neuron is isolated from a squid. A squid is a sea animal whose axon is extensively used in experiments for its huge diameter. Anyway, this axon is placed in a saline solution and connected to an oscilloscope that will record the membrane potential of this axon both at rest and after being electrically stimulated by the stimulating electrodes. We will use this simulation to observe the results of this experiment. When the recording microelectrode is inserted into the axon while at rest, the screen of the oscilloscope will record a constant resting membrane potential of -70 millivolts. Let's press this red button to electrically stimulate the axon. See how the membrane potential changed? It is no longer constant at -70 millivolts, is it? If I slow down the recording of the oscilloscope, you will observe such a variation. You must be asking, what happened? Why did the membrane potential change upon stimulation? What is the origin of this variation? All these questions will be answered in this document. Actually, the variation in the membrane potential that happens following an effective stimulus is known as action potential. And before I start answering all different questions that you have about action potentials, let's go back to the axon of a neuron. I want to introduce two new membrane proteins found in the membrane of an axon of a neuron. You already know about one type of ion channels. They are the sodium and potassium ion leak channels that are always open and allow the continuous passive diffusion of sodium and potassium ions along their concentration gradient. But actually, these are not the only sodium and potassium channels found in the membrane of a neuron. There are also the voltage-gated channels. What does voltage-gated channels mean? It is a channel that only opens when a certain voltage is reached in the neuron. If not, the channel will stay closed. The voltage-gated sodium channel shown in red here will only open if the voltage exceeds -55 millivolt, but it will soon close when the voltage reaches 30 millivolts. On the other hand, the voltage-gated potassium channel will open when a voltage of 30 millivolt is reached, but will close again when the membrane potential decreases back to -70 millivolts. You must be asking, how will understanding these channels help me understand the action potential? Okay, let's repeat the experiment of document A, but this time, let's simultaneously observe the behavior of these channels and their effect on the distribution of sodium and potassium ions, and thus their effect on the membrane potential. The neuron in this simulation is at rest for now. You can see how the resting membrane potential is -70 millivolts. Sodium ions in blue are diffusing through sodium leak channels into the neuron, while potassium ions in green are diffusing through potassium leak channels to the outside. But the sodium-potassium pump powered by ATP is forcing sodium out and potassium in. Notice that at rest, both sodium and potassium voltage-dependent channels are closed. I will hide the leak channels and the pump so that you can concentrate on the voltage-dependent channels, but if you don't see them anymore, it doesn't mean that they have stopped working, okay? Now, when I press the red button to electrically stimulate the axon, please observe the behavior of the voltage-dependent channels. Please notice the recording of the oscilloscope at the same time. Is it too fast for you? You see, upon a stimulation, the membrane potential of an axon increases, and once it exceeds -55 millivolts, the voltage-dependent sodium channels will open. This will cause an increase in the inflow of sodium ions. Since those ions are positively charged, the neuron will become less and less negative until it becomes positively charged and its membrane potential increases to 30 millivolts. This is referred to as depolarization. Since the neuron is not polarized as before, with the negative pole being out and the positive pole being inside the neuron. But now that the membrane potential has reached plus 30 millivolts, the voltage-dependent sodium channels close, while the voltage-dependent potassium ion channels open. This will increase the outflow of potassium ions to the outside of the neuron, and since potassium ions are positively charged just like sodium ions, this will reduce the membrane potential back to -70 millivolts. This is referred to as repolarization since the neuron returns to its initial state of polarization. But the potassium channel takes a little longer to close, which leads to an overflow of potassium ions outside the neuron. This causes a further decrease in the membrane potential to -80 millivolts. This is referred to as hyperpolarization. If you are asking now, but how is the resting potential retained again? Remember that it's the sodium-potassium pump that will return the ions into their initial distribution and the membrane potential back to its initial resting value. All the three phases, depolarization, repolarization, and hyperpolarization, make an action potential, that is a nerve impulse or signal. But remember that this action potential is only generated if the stimulation was enough to increase the membrane potential above the threshold value, which is -55 millivolts. So, to sum up what you learned about action potential today, action potential is a modification in the membrane potential of a neuron. It's caused by an effective stimulus that increases the membrane potential beyond -55 millivolts, and the origin of this action potential is the modification in the permeability of the cell membrane to sodium and potassium ions. Assalamu alaikum.